Cool. They got the graphic. Usually it's just a still image because they switch it to PDF. So that's nice. Thank you all for coming. Let's have some fun. So yeah, Plasma is pretty cool. It's what we're using to kind of build on top of an underlying blockchain so that we can scale it to support what we're trying to do. I'm going to dive a little bit more into what that means down the road. Here goes. So, blockchains. Why are they so important? Why are public blockchains so important? And it really comes down to being essentially a new way to look at truth. Truth is very important, but up until fairly recently, it's been localized and centralized. So essentially, everyone has their own truth, but there hasn't been a global truth, a truth that anyone has access to, that anyone can add to, and that everyone agrees upon. And this is super, super, super valuable. And so not only do we have this truth that you can see, but then essentially anyone can operate on it. I work most closely with Ethereum, so I'm going to be using that most of the time. But this is really applicable to any public blockchain. So yeah, it's really wonderful. And what this means in practice is that someone who lives in one part of the world can essentially transact and interact with someone in a completely different part of the world who they had no previous contact with without having to rely on trust. Because as opposed to having to trust your counterparty, you're essentially transferring the trust over to this public blockchain, this global truth. And so when you're transferring over this trust, you essentially have to make significantly less assumptions, because you're making assumptions that this public blockchain that you can see functioning will keep functioning as expected. You have to make honest majority assumptions with regard to mining hash power or with regard to validators, if we're talking about proof of stake. But both are significantly better than having to trust an individual counterparty, particularly when we're talking about these interactions. A lot of the time, we're talking about single games, right? So there's no real incentive for your counterparty to be honest if they will never interact with you again. They should just maximize their expected payoff in one game. As soon as you transfer over to public blockchains, not only do you transfer the trust, but it actually it makes it easier to have iterated game. So you can start getting collateral involved. You can start having reputation on this public ledger. And that's really cool too, because it can essentially turn a lot of your single games into iterated games, which is super valuable. Because as soon as reputation becomes involved and these games become iterated, it essentially disincentivizes counterparty risk. It makes your counterparty less likely to misbehave. And so we have this absolute truth, and I kind of think about it as this global perspective that anyone has access to, as opposed to, as I mentioned before, this relative truth. So Alice and Bob, or me and this lovely gentleman right here, can interact. We could play a game, we can have dinner together, and we're constantly exchanging information. But the information that we exchange is only between us. And for a lot of things, that's okay. My dinner conversation, I don't necessarily want that to be on a public blockchain. It doesn't really need to be on a public blockchain. Relative truth is good enough here. But then all of a sudden, during our dinner conversation, if we decide to make a wager, if there is more at stake, now all of a sudden I want a record of this wager. I don't just want to trust him to follow through if I win. I want to put this on a public blockchain so I have guarantees if X happens, I win, I receive this, and I have significantly more certainty about that outcome once it's on a public blockchain. So relative truth, absolute truth, important to differentiate between those. And then after you start thinking about that, if you want to build on a blockchain, I highly recommend you think very carefully about what you actually need to store on a blockchain, right? Because public blockchains are excellent, excellent for storing information, excellent for giving you certainty about execution once we get into kind of the realm of smart contracts, but they're very expensive. Ethereum is currently single-threaded, so you essentially write global computer, but it's single-threaded, so everyone's transactions are processed by everyone running an Ethereum full node. And so this essentially adds up very quickly. And so you want to be very careful how you're actually using public blockchains. What do you need to use them for? And then easy solution is just to use a hash, right? Because do you need to store an entire book on the blockchain, or do you just need to store a record of it so that when I send you the book, all of a sudden you can hash it yourself off-chain and check to make sure the hashes match, and then you have guarantees that the book you're reading is the same one I wrote. There are many examples like this. So if you think carefully about how you're architecting your decentralized applications, already without any layer 2 solution, you can get significantly farther than a lot of the dApps functioning today. And an important thing to remember when you're considering, what do I really need to have on-chain, is you want to remember that there are always trade-offs, right? It may be nice to have certain information on-chain, but maybe it's not worth the cost. Or maybe Ethereum isn't the right blockchain for you. Maybe right now it's too slow, and you would rather choose a blockchain that has essentially made different trade-offs. Maybe it's less secure, but maybe it has higher throughput. And so you've built your decentralized application, and now what? Now, you essentially need to scale it because it's wonderful. You have users, but now you run into the problem that a lot of dApps run into once they have everything ready to go and have actually deployed onto mainnet. The blockchain just can't keep up. And so first you look at other blockchains, and there are some to choose from right now. Some are launching, some have been launched, and there are many more being built. Right now, there are many different groups of people who see the potential of public blockchain technology and are essentially trying to get in at the ground floor and cement themselves as the blockchain. I don't really see this as happening because, as I mentioned before, there are always trade-offs. And so I find it very unlikely that one blockchain will essentially rule them all. I see there being multiple blockchains coexisting, and as interoperability improves, people will have to think less about what they deploy on because they will actually be able to transfer information, transfer state from one blockchain ecosystem to another blockchain ecosystem. This is currently possible through things such as atomic swaps or state channels, but it's still not widely used. Just because right now the cost is fairly high. With atomic swaps, we're talking about capital lockup costs. With state channels, they're amazing. They offer instant finality. But quite frankly, they don't scale that well once you have to have multiple users. Then you have to start thinking about more Lightning-esque solutions where you have a bunch of, essentially a network of state channels as opposed to everyone in one state channel. So this time, you've decided to stick with Ethereum, and then you get into the choice whether you want to do leverage layer 1 scaling or layer 2 scaling. So the way I think about it is that layer 1 scaling actually scales by extending validation. So you have these other blockchains. So now your base layer is no longer single-threaded, but it has the same security assumptions as the same security guarantees as, say, mainnet Ethereum today. And this is achieved through an honest majority assumption and random sampling. So you essentially randomly select a subset of your total validators, and they validate this shard. They validate this shard. So yeah, that's essentially how you spread the base layer security. And then we get into layer 2 solutions, and those are essentially piggyback off of layer 1. So yeah, they're pretty awesome. You actually have to worry a lot less because you make the assumption that your layer 1 is working properly. And so sharding, multiple base layer chains, and then layer 2 solutions on top of blockchains. And so the most common layer 2 solutions are state channels, plasma chains, and then side chains. And once again, each of these has very different trade-offs. So yeah, side chains, essentially, if they rely on their own consensus mechanism, their own way of making decisions. So if a side chain breaks, you're essentially screwed most of the time. And oftentimes, funds can be stolen or misallocated. Plasma chains are their own blockchain, but they are actually piggyback off of the security of a base chain. So a plasma chain has its own system for making decisions, but you're only relying on it to protect the plasma chain against disruptions, as opposed to for security. And so this is a step in the more secure direction. The trade-off is that because you have these new security guarantees, you actually have to be tracking the plasma chain state on another chain. In our case, we're using Ethereum. And this can actually get really tricky. As state transitions become more complex, keeping track of who owns what is actually very difficult. And then we have state channels. State channels are wonderful for a lot of things, but as I said, as you get into more parties being involved, or if you want to minimize capital lockup costs, yeah, you may just weigh the trade-offs. Some pros, instant finality, some cons. But I'm going to focus or just hit a bit more on Plasma today, because that's the scaling framework that we're focused on at OmiseGO. And so Plasma essentially plopped down in the form of a white paper. And it was super wonderful because it essentially granted scaling with relatively little loss of security. But it was a fairly big vision. And so since then, myself and a bunch of wonderful researchers have actually worked on breaking it down. And there have been quite a lot of interpretations and variations of Plasma since the initial publishing of the white paper. And a few of these flavors are Plasma MVP and then Plasma Cash. And the majority of the architectures proposed fall into these two subcategories. And then I would say there's one more category, which is essentially Plasma with general state transitions. So this is essentially trying to mirror, say, the EVM's functionality with those more complex state transitions, but on a Plasma chain. And significant progress has been made in all three categories. Yeah. Right now, we're currently going down the route of Plasma MVP, but we're exploring Plasma Cash and very open to a more generalized Plasma down the road. We're fairly lucky in that though decentralized exchange functionality can become complex, the actual function calls, the actual state transitions that are required for like a minimum viable product, and then even for it to get more complex, are relatively simple composed to, say, the functionality that the entire EVM has. Just because all of a sudden you're dealing with a Turing-complete machine, and lots of scary stuff can happen. Cool. So the way I think about it is you have a plasma chain, and that's a root chain smart contract. It's a smart contract for us on Ethereum. And this essentially holds users' assets. And then they can transfer those assets, that value, around on a plasma chain. And then when they're ready to exit the plasma chain, they send the transaction to the root chain smart contract. And then they are able to get their assets back on the root chain. And so Plasma MVP essentially has all these assets pooled together. With all types of Plasma, you have a full reserve. But with Plasma MVP, you have all of these assets pooled together. And this is awesome because it grants fungibility very easily. But the downside to this is that if one invalid transaction is processed, if one invalid exit is processed, the malicious actor, the bad party, can actually steal all funds in the smart contract. And so this is very dangerous. And because of this, all users have to be watching the Plasma chain to make sure it's still valid at all times. Then we get into Plasma Cash, and we're essentially breaking everything down into small chunks. So when I deposit my funds into the root chain smart contract and then get them back on the Plasma Cash chain, I essentially only have to watch this chunk as opposed to the entire chain, because essentially now the root chain smart contract does not have a full pool. It has a bunch of small pools comprised of these chunks of value. And so I only have to watch my own value. And so this is significantly easier for me because I don't actually care if an invalid transaction, an invalid exit is processed, as long as it's not stealing my own value. And this goes for everyone using the Plasma Cash chain. So yeah, this is a pretty cool property. Now I'm going to get into why we're going towards proof of stake. Why isn't an operator-run Plasma chain good enough? After all, you're only depending on this operator to protect against disruption. And the advantage of an operator is that if you have one party essentially having to run the entire chain, you can essentially require them to have a super beefy computing setup, and then boom, TPS goes through the roof. That sounds good, but there are actually some significantly downsides to that. And the two big ones are essentially censorship and resilience. So right now we have Bob, and he's a single operator. And we have Alice, and she's having a blast. She's enjoying her super cheap transaction fees because she's just started using Plasma instead of Ethereum directly to transfer value around. And so Alice sends transaction. Bob includes it in block. Now it's in the Plasma chain. And now the Plasma chain block is actually included in Ethereum. Alice sees all this, and boom, everything's good to go. But then Alice sends another transaction, but this time Bob doesn't like Alice's transaction. This is a transaction that will be detrimental to Bob. It will essentially hurt Bob in some way. And so he, as the single operator, chooses not to include this transaction. And there's not much Alice can do here because Bob is the only one who gets to choose which transactions are included in this Plasma chain. And so her only option at this point would be to exit the Plasma chain and join another one. But what if there were 3 Bobs? And this is just a simple example. When we're actually talking about proof of stake, we're talking about many more than 3 validators. But essentially, as you get more people getting to choose which transactions get included, censorship becomes significantly less of a problem because more people have to agree to keep a transaction out. And this is especially important when we're talking about serving the people that blockchain technology, that public blockchain technology is really supposed to be serving. The people who are not able to pay Bob off, who are not able to organize against an operator or a group of operators colluding. And so, yeah, by switching over and doing proof of stake, we get censorship resistance. And it's a lot harder, essentially, for all the Bobs to agree and not include Alice's transaction. Also, on the resilience side of things, just because we're relying on Bob as the operator, essentially Bob can invalidate the plasma chain at any time and force everyone to exit. And so if you're relying on this plasma chain for a business use case, this is horrible. Because all of a sudden, boom, plasma chain down because Bob doesn't like what your business is doing, or he just wants to hurt the network as a whole. And then you have to exit and enter a different plasma chain, which is, it's not a super costly process, but it will definitely cause disruption to your business. And so to minimize that, we have a bunch of validators who actually have to agree on what gets included in the plasma chain, so that if Bob wants to invalidate it, he can't on his own. He has to get many more parties involved. So what? Why does this stuff matter? And it's really because Alice and Bob are awesome, but Alice and Bob have had essentially fairly good lives. So I would say this technology is primarily, it will make Alice and Bob's life better, and Alice and Bob are the early adopters of this technology and the ones it's benefited the most so far. But really this technology, I see it benefiting not the people in the city, but the people living on the edge of the city. Essentially, there are a bunch of informal economies around the world who don't have access to traditional services, right? I have plenty of bank accounts. Right? Blockchain making finance faster is convenient for me. Great, I can transfer value faster, but I can already transfer value pretty well. If anything goes wrong, I can call my bank. They tell me exactly what's going on. It's decent for me. There are many people who don't even have a bank, and those are the people where I see crypto, I essentially see crypto really helping those people, because it essentially provides them with another on-ramp. So they can have access to financial services without having to go through traditional finance, which is very exciting. Now, real quick, in terms of adoption, right now, everyone's heads down building. I mean, that's kind of the nice thing about the hype going away for a little while, is that everyone's focused on building, because as blockchain technology kind of grows and becomes more popular, more people want to use it, which is why we need these scaling solutions. And so a lot of times when we talk about adoption, the common things to say are essentially like, before we get mainstream adoption, it needs to be faster. We need better UI. It needs to be safer. I wrote safer again because it really needs to be safer, or at least that's what some people say. And the kind of vision that at least was sold to me when I initially got into blockchain was eventually Alice will be using her smartphone and she won't even know that the underlying technology is blockchain technology. She'll just use it normally and get all this value from blockchain technology without even having to know about it at all. And initially, I thought this was super cool. But I really don't see this happening, because as I said before, there are always trade-offs, right? When you're dealing with public blockchain technology, there's a trade-off for doing so. And so as opposed to getting normal people to use blockchain technology without even knowing about it, I want to turn them into crypto people. I want us to teach them about why using a public blockchain to secure certain parts of their life is better and why they should appreciate it. They don't need to know how all the technology works, but I think it's very important for people to understand and value the trade-offs as soon as we start talking about financial sovereignty and essentially privacy. Cool. Yeah, that's me. Path is open. This field is so young. Get building. Cool.